The different thermodynamic processes are 1. Constant volume or isochoric or isometric process. When a gas is heated or cooled in a completely closed vessel, there is no change in volume but increase or decrease of pressure and temperature.
2. Constant pressure or isobaric or isopiastic process. The process when the physical change of the state of system at constant pressure is known as isobaric process. During constant pressure process, volume and temperature increase when heat is supplied to the system and decrease when heat is rejected by the system. 3. Constant temperature or isothermal process. When a system suffers a physical change under the conditions that its temperature remains constant throughout the process, it is called isothermal process. The essential condition for an isothermal process is that the system must be contained in a perfectly conducting chamber and the changes should be slow enough to ensure free exchange of heat with the surroundings. For reversible adiabatic or isentropic process. When a system undergoes a physical change under the condition that no heat enters or leaves the system during expansion or contraction is called isentropic process. The physical quantity which remains constant during an adiabatic process is called entropy of the system. 5. Polytropic process. Polytropic process is an approximation to real process. In this, volume and temperature do not remain constant and there is an interchange of heat between the gas and the surroundings.
The representation of constant volume process are shown in pressure volume diagram and temperature entropy diagram.
The governing equation for constant volume process is P, divided by T equals a constant. Where P is the pressure and T is the temperature for a process 1 to 2, P1 divided by T1 equals P2 divided by T2. Since there is no volume change, the work done by the process is zero, and applying first law of thermodynamics, change in internal energy equals m into Cv into T2 minus T1.
Since work done is zero, according to first law of thermodynamics, heat transfer during this process equals change in internal energy. Constant pressure or isobaric process. The isobaric process pressure volume diagram is shown here.
The temperature entropy diagram of isobaric process is shown here. Since pressure is constant in isobaric process, the governing equation for the process 1 to 2 is V divided by T equals a constant. That is V1 divided by T1 equals V2 divided by T2. constant temperature or isothermal process. The pressure-volume diagram of isothermal process is shown here. The temperature-entropy diagram of isothermal process is shown here. The governing equation for isothermal process is PV equals a constant. For a process 1 to 2, P1V1 equals P2V2.
Reversible adiabatic process or isentropic process. The pressure-volume diagram of adiabatic process is shown here.
The temperature-entropy diagram for a isentropic process 1 to 2 is shown here. The governing equation for isentropic process is PV rise to gamma equals a constant and TV rise to gamma minus 1 equals a constant and P rise to 1 minus gamma T rise to gamma equals constant. The pressure-temperature relation of isentropic process is P1 by P2 equals T1 by T2 the whole rise to gamma divided by gamma minus 1.
The pressure volume diagram of Carnot air refrigeration cycle is shown here. Process 1 to 2, adiabatic compression. Process 2 to 3, isothermal compression. Process 3 to 4, adiabatic expansion. Process 4 to 1, isothermal expansion. This cycle is repeated. During process 4 to 1, the heat is absorbed in the space to be cooled, and in process 2 to 3, the heat is rejected.
The Carnot refrigeration cycle in temperature, entropy diagram is shown here. Coefficient of performance COP of Carnot cycle is the ratio of heat absorbed to the work input in the cycle. It is the ratio of T1 divided by T2 minus T1, where T1 is the lowest temperature and T2 is the highest temperature in
The
Carnot
schematic
cycle.
arrangement of air refrigeration cycle working on Bell-Coleman cycle is shown here.
The pressure volume and temperature entropy diagram of air refrigeration cycle working on Bell-Coleman cycle is shown here. The coefficient of performance of Bell-Coleman cycle is T4 divided by T3 minus T4.